First, I will talk a little bit about the motivation, where we still have geometric complexity issues, the research that ultimately led to the new shader types, how we integrate them into the new APIs, and the examples, some examples. So motivation. Now, the previous talks and in general, we talk a lot about shading and improving shading and dealing with shading performance optimizations. But a part of it is still, how do we deal with a lot of geometry? And especially in VR, it's really beneficial to have very high detailed geometry because you get all the silhouettes and everything much more accurately. So it would be nice if we had a more efficient way to draw a lot of small things, and because our world, well, this room is probably not a good example, is made of many small things, but let's imagine all these panels or even better, the nature with all the undergrowth and rocks and debris and spaceships with lots of detail objects on top of them. But we can also look at other use cases where geometry is relevant and many small things can exist, like when we generate marching cube surfaces from volumes, or when we render lines, so with triangle strips, so that we have a lot of flexibility in how our lines should look like. When we render glyphs, they're like covering triangles that mask out the vector art, or when we render proxy objects for occlusion cutting, but also in applications that, for example, in CAD or electrical engineering, when you have lots of shapes that are, nuts and bolts or parts of other hardware that are massively instanced. But it's not just instancing many small things. We can also think of very large triangle meshes, and especially in CAD, we deal with millions of triangles, and unfortunately, we can never show you the really big models where, there's entire real aircrafts, not simplified versions, or ships and factories with tons of machinery, where the assemblies, go up to billions of triangles in the end. And in VR, we want to be able to just look at something up close or far, and so the tessellation has to be fairly high to deliver that. So tons of triangles which stress our geometric pipeline. In general, we have two directions to attack this problem. We can look at making our rendering more efficient. So let's use instancing, let's use multi-draw indirect, occlusion culling, whatever, to render our lots of data efficiently. And at some point we might, then we as a hardware company look at the fixed function blocks that are still part of the rendering pipeline. On the other side, we can improve the geometric programming model. We know, the geometry shader didn't truly work out to deliver a lot of nice flexibility and so on. The tessellation shader is very efficient at certain patterns, so certain types of tessellations. It distributes the workload very efficiently across the chip. So that worked nicely for some use cases. The compute shader indirectly gives us a lot of flexibility because you can generate about anything you want with it, but you kind of have to generate first and then store it somewhere and then render it in the end. So if we look at the hardware in a bit more detail, when you render something, you provide typically the hardware an index buffer, where your triangles are stored, and our primitive distributor sits on top of the pipeline and basically chunks this triangle buffer into many smaller batches for the hardware to process. So these end up being your vertex shader batches that are then processed by the many streaming multiprocessors on the GPU. Once vertex shading is done, we have another unit which figures out, okay, those triangles need to be actually rastered and others are outside the frustum, or they're back facing, or what very often happens with CAD models that we have so many tiny triangles that they're actually below the sampling grid. So yeah, at the end we have this VPC unit removing it. Now, we could add more of the red guys in the hardware to make things faster, but we have a lot of the green ones. So let's investigate and how we can make better use of them. And it's also just, our chips will just add more and more shader units. If we look at the hardware primitive distributor in detail again, so index buffer, I just created some non-zero number values to make it a bit more, stick out a bit the different numbers. So we have two primitives out of these vertex indices. And every time you render, so every frame, our hardware then figures out a batch of unique vertex indices. So up to 32, which reflects directly our 32-thread warp hardware architecture. Along with that, it creates a smaller in-pipeline primitive batch, which is now very similar to the original index buffer, just that the indices now reference the unique vertices that we have within this smaller batch. So the indices on the bottom, they don't need to be like 16 or 32-bit because the batch is only 32 primitives, a few bits are enough. So that green data basically is what the hardware eventually works with as we shade and rasterize and so on. But it's kind of unfortunate that we do this work all the time, right? And a lot of our geometry is the index buffer is actually never changing. I mean, we have a lot of geometry that we don't break into triangles. It's static most of the time, which led to the research and what we call meshlets is essentially, meshlets are these tiny pieces that we, chunk the bigger mesh into smaller batches. And the idea is that we pre-generate this information. So instead of having the hardware do it all over the time, every time, we just do it ourselves once and upload it as new buffers. So we have 3 new buffers that replace our classic index buffer. One that describes our meshlets, so how many triangles and so on every meshlet has. And the other 2 are the index buffers, and they, in the end, pretty much look very similar to what you saw before. Just now we filled those buffers ourselves, and we have many of them in a large buffer, or in those 3 buffers. And again, the indices are relative to each meshlet, so we can, the primitive index buffer, it's 8-bit or something is totally sufficient. The vertex index buffer still can be 16 or 32-bit. For every meshlet, we can also add additional information to cull the entire cluster of triangles, so the entire batch. Let's say we store a tiny bounding box or something with it. And those 3 buffers are actually smaller in most of the cases than our original index buffer. And why is that? We also do away with the limitation. So before we had a limitation that these batches had 32 vertices as maximum and 32 triangles. But now we go towards the ideal, which is twice as much triangles than vertices. And it's a bit visualized by these grids. So the top is basically more or less triangle count similar to vertex count, which is basically a triangle strip. And we can see, in the best case, a vertex is used by 3 triangles. And in the lower half, we have roughly, twice the amount of triangles than vertices. And in the intersection, our vertex is used by twice the amount of triangles. So the more vertex reuse, the better it is for the bandwidth, and we, save calculations and all that. And ultimately, this leads to the fact that, those 3 buffers are actually smaller than the original index buffer, because we reuse vertices much more efficiently. Now, how do we actually draw this? And the research, as Yuri mentioned, is a bit a while ago as it started. So the trend was we independently also came to the same conclusion as others at that time frame, that actually let's build an index buffer that contains only the surviving triangles. And we do this with compute shaders. So we feed the compute shader the data structures that you saw before, and they spit out an index buffer that we then render with the traditional pipeline. And this is, again, similar work exists from other game companies and researchers. And I also want to highlight one particular cool idea was by Sebastian Altonen, who kind of batched everything to 64 triangles. And then, because not every, as we cluster or break down a bigger mesh in these parts, not every part might actually need 64 triangles. So he filled it with degenerate triangles. But in our case, we actually do only store what we need. So we do allow the variability of these clusters. And we saw that, this is not on the new hardware, but some older hardware, probably Maxwell. To be frank, I don't remember when I took the values. But we saw that, when you have a lot of triangles that you do discard, these CAD models with super many sub-pixel triangles, that, then it can be actually a lot quicker, more than twice as fast as the old pipeline. But, it's not always the case that it's faster. So how does the compute shader look in detail? We set the amount of threads to the amount of vertices and spawn our work group. At the beginning, we fetch this one descriptor. We encode as much as we can in this 128 bits. And then we find out, okay, hey, this entire cluster is not needed, so we don't do any of the other processing. Then we load up our primitive indices, we load and transform our vertices, and we store them in shared memory, so that later, in the last phase, so then we wait, so we have all vertices now transformed in shared memory, and then at the end, our triangles, our threads operate on 2 triangles each, so this was the configuration used here, and fetch the vertices from the shared memory and find out if this triangle is visible or not, and then we output the surviving indices. So the cool thing here is that we can see that our threads in compute, because in compute our threads are our own, we decide what our threads do compared to the classic pipeline in graphics. So we can use them for anything. So in the first case, one thread had to load and cull the entire cluster. Another time we have one thread doing vertex work, and at the end we had one thread doing primitive work. So this is really nice and something we wanted to leverage in the future. Benefit of this is, it can be really fast because it's compute, it can run on any hardware. We also save on bandwidth because as vertices are not used, because they are never used when certain triangles are not visible, we save on fetching the other vertex attributes like texture coordinates, normals, and so on. Now the downside is that we have to come up with this machinery to create the index buffer culling and all that. And we have the problem that if we don't cull much, then we actually fetch things twice and we add a lot of work. And this ultimately was a bit of an issue. The other problem was that the early out mechanism doesn't really work so well because we have already created the work group on the chip. So when we run our compute shader, it will take up the 256 threads along with the registers, along with the shared memory, and then we find out, actually we don't need to draw anything. So for that time being, it prevents other work to be generated on the GPU, or less work to be generated. So wouldn't it be cool if we can somehow put all this into the hardware? So ultimately, this whole mesh shaders or mesh shading or this processing of taking some work and let multiple threads work on it is a trend that has already been started in graphics. With, for example, per pixel lighting, we moved to a tile-based approach where a compute shader operates on tiles, finds out which light sources are in it, and then runs the shading. So the threads within the compute shader already change the type of work they're doing. So they're finding out what light sources, and then they're actually doing the lighting. And all this is very, very flexible and very efficient. So here the same idea, when we go from per vertex processing to a group of triangles. Okay, the essential components, so the new shaders pretty much look like compute. So they get shared memory, you have yourself responsible for syncing the threads and all that. There is no fixed function fetch anymore, just like compute. You only get an index. This is the work group 10, and that's what you're working from, which also has the benefit that for procedural generation or whatever, you can just directly create your data implicitly. And we do allow one level of expansion. So that's the big difference to the compute index building thing before. Also that we allow you to have an additional shader that says how much work you actually want to create. And this is very similar to tessellation, where the patch control shader basically says how much to subdivide. And I will show you later how that works. Okay, and the rest is as usual, so your fragment shaders and so on, or pixel shaders, however you call them, you don't need to change them at all. So there is no difference here. Again, a little bit refresher, how is the compute shading model looking like? One workgroup ID comes in our case, so the compute shaders work on a 3D grid, but the mesh shaders essentially are just a 1D grid. So you dispatch them as a 1D grid. I need thousands or whatever workgroups to be spawned. Every workgroup has a bunch of threads. Now the new thing compared to compute is that they actually have an output. So they all have a common tiny bit of output memory, and the size of the memory depends on how you write your GLSL, how much vertex data attributes you want to pass to the fragment shader, and you can also allocate some shared memory and so on. So that's basically very similar to compute. Yeah, if we look at the evolution again a little bit, so vertex shader didn't have any information about the connectivity, so other triangles were not known. And the thread mapping was basically predefined. Yeah, you have one thread, one vertex. Then we had the geometry shader, which was able to operate on a primitive level, and one thread was one primitive or primitive strip. And as the illustration already shows, this might not really map so well to the hardware. If one thread does a lot of work and the others don't, this is in general not good for the SIMD processing. And the topology was also kind of very limited to just triangle strips. Also, we have to create a lot of vertices for every strip and in each thread. So yeah, that didn't work well. Tessellation shader does work well with the fixed patterns. So those are really fast. And we have a mapping of either one thread per patch or one thread per evaluated vertex in the second stage of the tessellation pipeline. Now with the mesh shaders, everything is awesome. So it's just like compute, super flexible. So everything is up to you. And so I have a bunch of threads creating a tiny mesh. So the mesh size obviously is still predefined by you in your shader. So you define, okay, I need 64 vertices, 128 primitives or something. And as the illustration shows, so they don't need to be connected, even though the bunny before always showed the nice connected clusters. It's a tiny index buffer, tiny vertex buffer, and how you use it is completely up to you. While we're at it, we also fixed something. So we added true per primitive output attributes. Now before, you had to go through kind of the fast geometry shader and calculate if you wanted to have something per primitive. And in the end, it was still kind of a vertex attribute that didn't have any interpolation and so on. But now you can say, okay, I want a certain value to be per primitive, and the fragment shader also sees that as a per primitive value. And typical things are like, triangle normal, but also if you think of selections or other mechanisms that you want a per primitive ID passed along. Okay, our traditional pipeline, as usual, we have the darker green are the things that are not really programmable. So the vertex attribute fetch is done by the hardware. Then come vertex shader, tessellation, control, topology generation if tessellation is active, evaluation, geometry shader, raster, pixel shader. The cool thing about the graphics pipeline compared to compute is basically we have all these shader stages, and all the memory that they pass between each other is kept on the chip. So we use the L1 and L2 cache to pass the vertex data or triangle data and all that across the pipeline. And it's also very cool because the hardware takes care of this allocation essentially for you, and also it gives back the memory once it's done. So if some triangle is done with rasterization, that memory is implicitly given back to the hardware, and new work can come in at the top. And obviously these are bigger buffers so that we have a lot of work in parallel. Now the new pipeline, which works in addition, so we're not replacing the old stuff, we just added something, is a bit streamlined. We have this optional expansion stage at the front, which can decide how much work you want to generate with a task shader. We call that task shader. Then comes the mesh shader, which creates these tiny index and vertex buffers, and the rest is as usual. And again, all the memory is kept on the chip as before. If we look at it in detail, so we launched some work. Our task shader is then run on every work group that we launched. The task shader has one output which is built in, the amount of children it wants to create. And you can pass anything up to 16 kilobyte to the children, so whatever you want. Then the mesh shader is run, and it can access the output of the task shader as well. And that output will survive as long as we have mesh children around. Every mesh shader can write how many primitives it's actually generating. So you pre-allocate a fixed amount, but then you can actually say, okay, I'm using 5 of the 128 triangles or something. So the variability is guaranteed there. And then the rest is as usual as before. So why this task shader? Well, it's really cool to not create work. Here again, we give you a new mechanism to quickly not do work. But the task shader can also be used not just in this terms of meshlets, and you can also use it to generate. So if you think of a line strip, you want a smooth strip, you can say, okay, I need that many amount of meshlets or triangles in the end to make the line smooth. Or if you have arcs or other geometry that you can procedural generate, you can say how much meshes you need for that. Because you're fetching all your data yourself, you're pretty much at complete liberty here. It can also create points, lines as well, so it's not just triangles. And we can completely disable the rasterization, so that's a feature that already exists. You can disable rasterizer, and then it gives you a compute tree. So you can actually have something like a compute tree, and here's a quick, very basic example. So let's say we launch 3 task shader work groups. Now, obviously, we would launch a lot more in reality, but then every task can say, okay, I need whatever amount of children. We allowed up to 64,000 children per work group. Now, you wouldn't want to completely imbalance your tree for performance reasons, but that many children would be possible as a maximum. The work group ID is always passed relative to the parent, so every child mesh knows which child it is. And we do give some guarantee how we create the work groups. So we guarantee that we launch them in order within the level. So a work group, child 5 will be launched before child 6. The execution order, of course, can be out of order the way the hardware is designed for maximum parallelism. We do give an output primitive ordering guarantee, so that the primitives, as you write the index buffer within the mesh shader, obviously are ordered, and we keep that order, and we also keep the ordering across children in this tree. Some implementation details. Okay, so currently the workgroup is 1 warp, so 32 threads. You can generate up to 256 vertices, up to 512 primitives. I highlight here some values which for allocation granularity reasons are what we are kind of recommending at the moment. But ideally you play a little bit and find out what works best for you. And the reason is that you have to play a little bit is that obviously if you had a really big mesh, that means you allocate a lot of resources on the chip, like if you have a lot of shared memory in compute. So we cannot run so many things in parallel. So you kind of have to balance the amount of vertex reuse, which saves you work and bandwidth, with how much actual work you can run on the chip. There's also this new feature I think we haven't really mentioned. So Turing gets barycentric coordinates as well. So there's a new fragment shader input that gives you the barycentric coordinates per triangle. And with that, it is possible that you can actually pass less than 32-bit data types from vertex or geometry stage to the pixel stage, because you could pass one, let's say, 32-bit value, which in fact encodes 8-bit values. And because you have the barycentrics, you can unpack from every vertex in the triangle those packed 8-bit values and then run an interpolation with the barycentric coordinate. So that allows you to make it smaller, and smaller the more we can run in parallel. And again, try to avoid crazy imbalanced trees. Okay, so on the software side, how can you make use of it? So DX12 gets NV API extensions. I'm not covering those here, also because they look kind of ugly. So it's much easier. I mean, OpenGL and Vulkan have native support for doing proper extensions, so it's much easier to integrate them into the shading languages. We introduced two new shader stages. You cannot mix them with the old stages, but the rest is pretty much exactly the same. We also create new draw calls that look very similar to compute dispatches, just that they're one-dimensional. There's the usual draw indirect versions as well, so where you can store the actual attributes, so how many tasks or how many meshes you want to generate in a GPU buffer and write it. And you can also, in this multi-draw way, pass how many of those dispatches you want to do and source the actual amount of work of different dispatches with the count version. And Turing also got much faster in this. So in the previous generations, we had a bit of an overhead. If, let's say, you only have 10 multi-draw calls active out of 1,000, we had a higher overhead. And now Turing can, if you have 10 out of 1,000, is much more efficient in skipping the other ones that you're not actually processing. So GLSL side, again, starts out like compute. So it's still three-dimensional defined because we just reuse the built-ins, but effectively 1D, you get a new output. The task count basically is how many children you want to spawn from the task shader. In the mesh shader, you start out similar to the geometry shader, defining how much resources you need, how big your arrays will be sized, what type of primitive you're producing. You have the primitive count and then the tiny index buffer. So it's defined as uint, but it actually is uint8. We also give you a bunch of new arrays for the built-in variables. So similar to a geometry shader, everything is now an array because it's tiny arrays. And there's also this new per primitive qualifier. So the per primitive values are now proper per primitive values, and you can define your own per primitive outputs, which is not shown here, but just by adding per primitive in front. And if you want to communicate between task and mesh shaders, there's this new task NV qualifier that says, okay, this is the memory you want to pass between the stages. And you can define that content however you like. Now, if we look at basic, very basic mesh shader, Yeah, we start out defining how much threads work we do. We fetch some, this whole meshlet thing is really, one way to do it. You can come up with your own encodings. But in this case, we fetch the meshlet descriptor. We transform every thread, transform one vertex, and compute some normal, or in this case, just fetches everything. And then we fetch the index buffers, and we do provide either direct access to the array, or we also give you a function that can write 4 indices at once, which is more efficient than doing it individually. So that way you can pre-pack your index even more efficiently. And then at the very end, you would write how many triangles in this case triangles, you're using. And only one thread would have to write that information, but as long as all write the same value, then it wouldn't matter either. Okay, so let's look at some concrete samples. So the first one is basically a big cat model, actually our own, finally, some data coming from ourselves. It's a DGX station with a bit less than 40 million triangles. And I will show it in a second. And so this will be an open source sample that you can see how the mesh and task shaders look like, but also it will give you boilerplate code to just generate all the meshlet data structures in advance, so that's easier to integrate for you. And the idea is that the task shader does culling, based on frustum, but also on the user clipping planes, and also on a backface cluster. So for every triangle mesh, we find out what the average normal direction is of the cluster, and then we have a cone angle because in this case it's just flat. But imagine you have some surface or part of a sphere. Then obviously you have normals going from across multiple directions. And so if you want to do backface clustering, you have to kind of know how far you have to be from the angle that you're guaranteed not to see any triangle anymore. So here, at either side, we are within that angle. If we are within the angle, then in the middle, then we see both sides. And if we are just on one, then we only see one side. Yeah, you can also cluster cull, if you find out you don't need the full accuracy, but let's say, this stuff is so far in the back, this tiny bounding box, that it's 2 pixels big, so I actually don't care anymore. And this also helps very, very much in CAD, that we, very often we can get away with culling, even if it's, more aggressive than subpixel. We squeezed everything in the meshlet descriptor at 128-bit, so the normal clustering and all that is encoded in 128-bit. Task shader does the work for 32 meshlets at once. So you wouldn't want to do one meshlet per single task shader, because you would kind of blow out a whole warp doing very little work. So it's better to do more work there. And the mesh shader is then fetching, transforming vertices, and we do allow per triangle culling as well, like we did with the index buffer building in the beginning of the research. But actually the hardware is still very fast at throwing away triangles afterwards. So this can be beneficial depending on how much you benefit from also not fetching additional vertex attributes. So let's say you have very fat vertices, so lots of texture coordinates, tangents, whatever, and you have a lot of vertices that don't contribute, then in theory I can also show it. In practical, it can save you additional work, but the most savings you get from the task shader. So because there you completely, skip all the allocation of the mesh on the chip and all that. So the better your task shader is at not creating work or creating only the work you need, the better it is. On the implementation in the GLSL side, obviously, not every hardware will have the mesh shaders. There's a lot of Pascal GPUs out there and less. So to make it easy, I think it is still relatively easy to have both vertex and mesh shaders around. So if you define your outputs, yes, you have to use a little bit of macros and hide that the one is an array and the other isn't. And you also would have to rewrite your vertex shaders a little bit so that you express them as a function of the vertex index. And once you've done that, then you write one code once that takes care of loading the meshlet, decoding it, and so on, and then calls your functions as it's required. And at that point, it's straightforward to switch between just the new way or the old vertex shaders. We also experimented a little bit with some optimizations because we want to maximize the amount of actual geometry within the meshlet. So there's algorithms that allow you to and this is good for the current hardware as well, that for vertex cache optimizers. So those algorithms can work quite nicely, but sometimes they can make the cluster culling worse, because the upper thing is basically straight from the CAD model, and because the CAD, in the way they tessellate, they give us really nice shapes, more or less, and that is pretty good for the cluster culling. But the optimizer, which in theory gives us less meshlets because it has higher utilization of meshlets, but it may give us worse cluster culling. And then there's one really, really big field that we haven't played with yet, but I think this will be one of the major one of the major topics around mesh shaders is compression. Because now you're in full control of fetching all the data yourself, and you have a warp, so a compute-like model at hand. You can encode the vertex and index data however you want, and you can use a bunch of threads to decode that data. And because you decode it only at the time you really need it, it's very efficient, because compared, if you were doing it with a compute shader before, you would still have to write it out somewhere and then render from it. But here, you directly come up with this decompression as you use the data. Okay, now I will attempt to show the thing running. Okay, so here's our DGX station, and we can play with the clipping planes. And this is the standard clipping planes in OpenGL, and we currently have the standard renderer active. So this is fixed function processing, but regular vertex shaders and such. And our performance is like 6 milliseconds. And now if I switch to the mesh shading, we are at 4 milliseconds, so we saved a good deal of work. And we can see some statistics. We are rejecting 40% of the meshets, and roughly the same amount of triangles in the task shader. Now, if I'm more aggressive with the clipping, then obviously the performance difference between the standard pipeline and the mesh shader is pretty dramatic. So, so the better you are at rejecting in the task shader, the more you get out of this new feature. But I'm not lying. I mean, if we enable or disable the clipping again, then we will see, so the performance is around 5 milliseconds, and here it's also around 5. But if we zoom in, then the frustum culling kicks in, so standard pipeline doesn't win anything, and the mesh pipeline wins a lot. Now, arguably, you can come up with, frustum culling, whatever systems, but here you have a granularity that is very fine and relatively easy to integrate in the pipeline. So you don't need as much machinery around it. I can also, we can colorize by meshlets, and when we activate the clipping again, I can also, these are all the culled meshlets, that were removed. And if we simulate so this will take a bit. So we simulate a fatter vertex where we pass more attributes to the fragment stage. And now so I disable the clipping again. We're at 9 milliseconds with the regular pipeline. With the mesh, we are, similarly. And we can enable the per primitive clipping, and now we are a bit better. And so if I zoom out even more, the difference is even higher because we save. There's so many sub-pixel triangles now that we save on getting that data. But again, it will depend on the use case. So obviously you have to play with it and see what works best for you. And the image here is still rendered super sample, so we still or downsampled. So it's not the actual screen resolution you see here. So it's actual 4K. Okay, when you saw the difference between when we are not culling a lot and standard pipeline, may not have been that great. And that's also because we improved Turing's regular geometry performance a good deal again compared to Pascal. So the numbers, so Pascal is also really good in regular geometry processing again. So other use cases are tiny draw calls. Obviously, like we started the presentation with the tiny nuts and bolts and leaves and rocks and so on. You might think, hey, we already have multi-draw indirect and instancing, but for the very small draw calls, like less than 512 triangles, or the bigger the chip, the higher the threshold of that number, then these are not as efficient as the task shader is now, because the task shader, similar to the tessellation, is able to distribute the work in a parallel fashion across the chip, while the instancing or multi-draw indirect scheme still, at the very top of the pipeline enters one draw call after another. So while the task shader, you have many task shaders running, they generate the work and it gets orchestrated across the chip. So for tiny draw calls, this is really something to look at as well. I focused a lot on culling, but you can also make LOD decisions in the task shader. The task shader can define in its output. The task shader finds out, okay, the object is, 20, 30 pixels on the screen. So let me pick these meshlets instead of the other ones in the next stage. So instead of 500 triangles, I generate only 50. It can make that decision. I mean, you can make that decision in the task shader and then load the appropriate data in the mesh shader. Okay, there's also the beloved line stippling. Cannot have a Quadro talk without mentioning stipples. So, as some APIs don't have stippling anymore, like Vulkan, this is a way where the task shader and mesh shader works really well. So, in one side, we directly let the task shader compute how many triangles we need. And so all the stipples are done in hardware. So every stipple is 2 triangles. And every arc is basically a task shader and every color is a meshlet along the arc. And in the other example, the stippling effect is done through a running UV coordinate. So we compute the UVs, so the distance along the circle, and it can be in any space you want, so because you're computing the distance. And then you could use fragment shader discard to actually, in this effect, the stipples are done with a black color, but you could use discard to make them disappear. And we also had a presentation at GDC a couple years, I don't remember, a while ago, where we showcased how you can do some of the calculations. And I will also quickly show it, but we can also use it for spaceship ribbons. So, very in the gaming, you have a lot of trail particle effects with running UV coordinates. So like fading out the color along the ribbon. And for that, it's also very useful to directly do it on the GPU. So here we can see, as the distance on the screen becomes longer or shorter along the arc, that's why the pattern is actually moving. The distance becomes longer or shorter because we are computing in 2D space and not in 3D. And so this is running on emulation, but I can also run it on hardware with the shaders directly. So how does it look like? I hope you can see this. Yeah. So we create the position along the circle. We then compute the distance compared to the next point on the circle, and every meshlet. So we use the shuffle instructions to find the next vertex along our meshlet strip, and we compute the running distances here with some warp reductions, and then because we know the meshlets are spawned in order, we can have an ordered lock, which we can compute ourselves a little bit. So we still need to do a spin lock, but still we have a guaranteed ordering, so this will not lock up the machine. And basically, the last thread has the longest distance of our segment along the arc, and we accumulate the distance of the last thread, and we get the distance of the previous meshlets because they're all still running independently. That way, then we get the accumulated value and add it back to our per thread values. That's basically the per thread distance coordinate, which makes the texture coordinate along the surface. Okay, so it's just an experiment or concrete example how to procedurally generate geometry, and we expect that there's many, especially if you think of architecture design or something, there's a lot of very primitive shapes that can be expressed procedurally that we think can benefit from the new shaders. So as a takeaway, 2 new shaders to play with, 2 new tools to create geometry on the hardware, on the chip. The technology is built upon our very good tessellation pipeline, so indirectly. So we can very efficiently distribute and create workloads across the entire chip. It adds to the existing pipeline, so we are not removing it, and we are not, use tessellation shaders when they're fast, but you can use these new things, especially if you do culling, but also, the new use cases like the compute trees, if you disable the rasterizer, so there's a lot of flexibility, and it's a new way that's more scalable across the chip. And that basically concludes my talk, and thank you very much.